If you're using AI agents for complex or multi-step tasks, you're probably very familiar with this. An AI agent starts off doing exactly what you asked, and then, step by step, it begins drifting, taking actions you never intended, wandering into tools it didn't need. And it's not just your agents. Even the best AI assistants like ChatGPT, Claude, and Gemini will wander unless you keep pulling them back on track. So why does this keep happening? Most advice today will tell you it's a prompting issue, that you need a more powerful model, or you should switch to a completely different agent framework. But the real problem goes deeper than that, and it isn't what most people think. Most AI agents today are built on a pattern called React, and that's exactly where the problem lies. So in this video, I'll show you the missing piece, a simple architecture layer that leads to faster, cheaper, and dramatically more reliable AI systems. If you're new here, I'm Fraser Dorado, and I've spent nearly a decade building large-scale enterprise systems. And today, through my AI and automation agency, I help teams design scalable, reliable AI systems. Everything I'll show you here comes from building the systems and breaking them in the real world. With that, let's first talk about the pattern almost every agent relies on today: React. React is short for reasoning and acting, and it's basically a loop where the model takes one small step at a time. Thought, action, observation, repeat. In practice, this means that the model thinks about what to do next, takes an action, looks at the result, and then repeats the process until it can answer the question or finish the task. That's the whole pattern. Now, React didn't come out of nowhere. It was trying to fix two problems. First, pure reasoning. Chain of thought with no tools. The model would reason in detail, but it couldn't query a database, call an API, or look anything up. And second, pure acting. Direct tool calls with no explicit reasoning. The model jumps straight to call this function, then this function, but you don't see the internal thought process. That makes it brittle, hard to debug, and easy to derail on multi-step tasks. Now React combines both, so that the model can think and call tools step by step. That's why it became the default mental model for agents. It's simple, flexible, and honestly, for a lot of interactive use cases, it works extremely well. But here's the catch. React is inherently reactive. It only focuses on the next step, whatever seems reasonable based on the last observation. And while that's great for discovery tasks or tasks that need to adapt on the fly, it often leads to suboptimal trajectories and long chains of unnecessary tool calls. That's when you start to see agents stray off the path, repeat actions, slow down, burn tokens, and drift away from the goal. Not because the model is weak, not because your prompt is wrong, and not because you chose the wrong framework. It's because the architecture never factors in a plan before executing. Now, don't get me wrong. React is a useful pattern. It's just not the pattern you should build every agent on top of. But if you want to see how I build a React-style agent, I've linked the video below. So if React's main weakness is that it only thinks one step at a time, then the obvious fix is to separate the thinking from the doing. That's where a plan and execute agent comes in. Instead of thinking before every action, the agent creates a clear plan upfront and then executes it. Here's how it works. First, a planner, usually an LLM, takes the user's goal and the available tools and turns that into an explicit step-by-step plan. Then an executor walks through those steps, calling the right tools, tracking outputs, and only checking back with the model when something is unclear or fails. That one change, separating planning from execution, makes agents dramatically more reliable. And it comes with real benefits: faster execution, lower cost, better results, and more predictable behavior. For long structured workflows like document pipelines, multi-system integrations, or business processes, this pattern is almost always superior to a reactive loop. It's still flexible, still adaptive, just more intentional. If this sounds familiar, it's because it's very similar to the orchestrator worker workflow pattern I showed in another video, which I'll link below. Now that you understand the idea behind plan and execute, let me show you how it actually looks like in practice. We'll walk through the pattern so you can see how it works. We're going to walk through the sequence diagram that represents the plan and execute agent. As you can see, it has the user, the planner, the replanner, executor with tools, and the memory of the state. You do see there's code on the right, which is the implementation of the plan and execute agent, and we will run and observe the output once we understand how it works. So for now, just focus on the sequence diagram. Let's take a look at the example. A user inputs a query like this. What are the combined box office earnings of all movies directed by the directors of the top 3 highest grossing films of 2023? Now that's quite a complex query, right? And that query is then handed off to the planner. The planner then analyzes and breaks it down into smaller subtasks. So it creates a plan sort of like this. So the step 1 is find the top 3 highest grossing films of 2023, then identify the directors of those 3 films. For each director, find all their movies, get the box office earnings for each movie, and then do a sum of all the earnings. This plan is first stored in the state and then handed over to the executor. So the executor first executes step 1. So it finds all the top films of 2023. It does a web search, gets the result. It then stores that in memory and reports the progress to the replanner. The replanner checks the current plan and the results. It notices that it's on track and then continues with the plan. Then the executor moves on to step 2. So it now needs to identify the directors. So it does a couple more web searches, as you can see here. And then it stores the directors identified into the state or the memory and then reports that to the replanner. But in this case, the replanner detected an issue. The plan assumed 3 directors but found 4. So it now updates the plan, stores the plan back in the state, and then hands it off again to the executor. So it can continue with the updated plan. Then it finds all the movies by each director. So it does a couple more web searches, stores all the films cataloged into the state or the memory, and reports back to the planner. Again, the planner notices another issue. It notices a missing film. It creates a new subtask or substep, hands it over to the executor again, executes a web search to find the missing information, gets the complete information, stores it back in the state, and then moves on to step 4. At step 4, then it needs to get the box office for each film. So it does a few web searches in a loop to get the box office amount. It stores the earning in the state and then reports all the box office data to the replanner. The replanner checks for any missing or unreliable data. Once it has validated and processed the data, it then indicates to the executor to proceed to the next step. And in step 5, it does the calculation. The executor retrieves all the earnings from the state. It gets all the box office data. It does a sum of all the amounts. It gets the total calculation, hands it off to the replanner. The replanner decides it has enough information to respond to the user, and it then responds to the user. Now let's quickly skim through the code that is going to execute what we discussed. As you can see here, we have the state, so the planner execute state, which has the input, plan, the planning steps, and the response. We have the planner prompt that basically says, given the objective, come up with a simple step-by-step plan. And then we have the executor agent. And here you basically can use a small parameter LLM because it's only going to be used for executing tools. And finally, we have the replanning prompt, which is similar to the planning prompt. It asks the LLM to come up with a simple step-by-step plan. And where it differs from the planning prompt is that it now also takes in the original objective, the original plan, and the current steps that have been followed. And it basically tells the LLM to update the plan accordingly if any more steps are required to be executed in order to solve the objective. And finally, we put this all together, and I'm using LangGraph here, so I'm generating the graph or the workflow in this case. I pass the state, I add all the nodes that are required, I put it together, and I compile the graph. And now I'm going to execute this graph so that you can see how the output relates to the sequence diagram that we just walked through. As you can see here, I've ran the plan and execute agent. I know it's a lot of text, but I just want you to see how it's actually executing it. So as you can see, it creates a plan, then it has to stores the past steps. Again, it revises the plan, stores the steps. It keeps doing this until it resolves or has an answer, and then it synthesizes the response. And here's the response. Pretty cool, right? And that's it. However, this version of the pattern does have one important limitation. Every task still runs in sequence. So if you have multiple steps that could run in parallel, they simply won't. And your total execution time ends up being the sum of all the steps. That's where the next two patterns come in, both of which improve on this in their own way. One variation is Review, which stands for Reasoning Without Observation. Review is designed to improve on React by planning the entire tool chain upfront instead of reasoning step by step. It does this to solve two main problems: reducing costs and execution time, and simplifying fine-tuning. Here's how it works. The architecture has three main components. First, a planner, This is an LLM that takes the task and generates the full multi-step tool plan in a single pass. Second, a worker. This executes each tool call using the arguments defined in the plan. And third, a solver. Another LLM that takes the original task and the collected tool outputs and produces the final answer. Only the planner and the solver require LLM calls. The worker just executes tools. This is what allows Revu to avoid repeated reasoning steps and reduce redundant token usage. Let's walk through the pattern so you can see how it works. Just like before, we're going to walk through the sequence diagram and then execute the code to see this in action. As you probably noticed, it has a user, a planner, a worker with the tools, and a solver. What is missing here is the state or the memory, which does exist, it's just not shown in the sequence diagram. And now let's walk through the example. As you can see here, the user makes a request, and the request is, what do the directors of the top 3 grossing films of 2023 have in common in their educational backgrounds? That's quite a complicated request because you need to solve for multiple things before you actually have the answer. So the user makes this request, and this request is handed over to the planner, and the planner creates a plan with placeholders. There's no tool execution yet. It creates a plan something like this, where it has a plan with evidence variables. So it first does a web search E1, and then E2, E3, E4 depends on E1. Similarly, E5 to E7 depends on the task before that. And once it has all that information, it can then solve the problem. So once it has generated this plan, it hands it over to the worker node. The worker node starts executing on this plan. So it executes task E1 first. So it does a web search, gets the answer for that. And then it executes the remaining 3 tasks in parallel. So it does a couple more web searches to get the information that it needs. Once it has those satisfied, it can now execute the next set of tasks, which were dependent on the previous ones. So it runs E5 to E7, again a few more web search to get the right information. And once all the evidence is collected, it then hands it over to the solver. The solver receives the plan and the actual observation, and it analyzes this evidence. After analyzing this evidence, it finds out that they do have actually a common background, and the solver decides that this is enough to answer the user query. It synthesizes a response and then returns that back to the user. Now let's quickly skim through the code that is going to execute what we just discussed. As you can see here, we have the state, then the state maintains the task, the planning string, the steps, the results of each step, and the final result. We then have the prompt or the planning prompt, which basically says, for the following tasks, make the plan that can solve the problem step by step. And for each plan, indicate which external tool with tool inputs to retrieve the evidence. We take that and we make a planning step. So basically call the prompt with an LLM. And then we set up the solver prompt, which basically says, solve the following task or problem. It has the input, which is the plan, and the task that were executed. And finally, we put this together in the graph. So I'm using LangGraph again, generate the nodes that are required, compile the graph, and then I'm going to execute it so that we can actually see this in action. As you can see here, I ran the Revu agent, and it generates a plan with variable substitution placeholders. It then starts executing that plan and storing the results in results. So as you can see, it keeps growing. Once it has all that information from executing all the tasks, it then synthesizes the response, as you can see here. That's it. But like any architecture, Revu isn't perfect. Here are a couple of limitations to keep in mind. First, limited environmental context hurts planning. If the agent doesn't know enough about its environment, its tool choices won't make sense. However, you can improve this with few short examples of fine-tuning. And second, most tasks still run sequentially. So even though Revu saves tokens, your overall execution time is still the sum of all those tool calls. Which brings us to a pattern designed specifically to fix that, the LLM compiler. This one is designed to speed up agentic workflows by turning the plan into a DAG, a directed acyclic graph, and eagerly executing tasks the moment they are ready. Here's how it works. The agent architecture has 3 main components. A planner, which streams out a DAG of tasks, including their dependencies, a task fetching unit, which schedules and executes tasks as soon as their prerequisites are completed, and a joiner, which returns the final result to the user or triggers a second planning round if needed. This approach is incredibly efficient, especially when you have independent tasks that can run in parallel. That means you get faster parallel execution, fewer redundant LLM calls, and much lower token usage overall. Let's walk through the pattern so you can see how it works. Again, just like before, we're going to walk through the sequence diagram and then execute the code to see it in action. As you probably noticed, we again have the user, the planner, the task fetcher, executor, tools, and joiner. What's missing here again is the state, which is present, it's just not shown in the sequence diagram. Now let's walk through this example. As you can see here, the user makes a request, and the request is compare the price of iPhone 14 Pro across Amazon, Best Buy, Walmart, and Target. Which store offers the best deal, and what's the price difference? If you think about it, this is quite a complex query, right? So this query is then handed over to the planner. The planner generates a DAG with the task dependencies. So it looks something like this, where you have a couple of tasks that can be run in parallel, and there are a few tasks that are dependent on those independent tasks. This DAG is then submitted to the task fetching unit, which analyzes the DAG for ready tasks, and then moves into phase 1, where it starts executing all independent tasks in parallel. As you can see here, it does a couple of web searches. After it's got all the information that it needs, it unlocks new tasks, and then it moves into phase 2, where again it dispatches tasks like find minimum, where it gives all the information that it has from above, it synthesizes a response, and then stores that response. It also finds the maximum, as you can see here. Once it has all the information, it does the final task. It calculates the difference with the help of the joiner. It stores that result, and once all the tasks are complete, it joins the final result. The joiner then decides if it has enough information or if it needs to do any other steps. If it has enough information, it synthesizes the response and gives that back to the user. Now let's quickly skim through the code that is going to execute what we just discussed. As you can see here, we have a pretty simple state, which maintains the history of all the messages. We then have the planning prompt, which basically consists of the number of tools and tool descriptions and guidelines on how to generate the DAG of tasks. We then create a planner, which takes in the LLM, the tools, and the prompt, followed by creating the task fetching unit, which is basically the plan and schedule here. It takes in the messages or the tasks, and it then schedules them so that it can be executed as soon as the dependencies are resolved. From there, we create the joiner prompt, which basically says, solve a question answering task. Here are some guidelines on how to do it. Finally, we put this together. Again, I'm using LangGraph here. So we're going to input the state, create the nodes, and then compile the graph. Now let's execute this so that we can see this in action. As you can see here, I've ran the LLM compiler. And with this print statement, you should be able to see what exactly is happening. So it starts with planning the tasks and then scheduling them. Once the tasks are scheduled, it then starts executing them. So as you can see, it's processing task 1, 2, 3, 4. You can also see the query for each task. Once it has processed all the 8 tasks, you can then see the dump of the entire message history, and it provides the observation from all the 8 tasks to the joiner, which then synthesizes the final response. As you can see here, the cheapest is Amazon and the most expensive is Walmart. That's it. But like every architecture, LLM compiler comes with a few limitations. Planner output parsing can be fragile, especially when functions require multiple arguments. However, streaming tool calling would make this more robust. Variable substitution is delicate. However, a more reliable syntax or a fine-tuned model can help here. And finally, the state can grow very large. If you need multiple replanning rounds, your message history can explode. And you may need a message compressor once you cross certain token thresholds. So again, like everything in agent architecture, it's a trade-off. The right pattern depends entirely on your use case. Now you've seen how different agent architectures approach reliability in completely different ways, and why most failures aren't caused by prompts or models, but by the underlying structure. Once you start seeing the systems in this way, you start engineering agents that behave predictably, scale smoothly, and stay aligned with the goal. If this breakdown helped you finally understand why agents drift and how to build architectures that keep them on track, you're in the right place. For more deep dives into building AI systems like this, hit subscribe so you don't miss the next one.